So welcome everyone. I'm Ilya. I work at Teralytics. I'm a front-end and data visualization developer, and I will be speaking about what we are doing at Teralytics and what tools we use for that. In particular, the ClickHouse database, which allows us to do scalable data analytics. Yes, so Teralytics is a relatively young company. We are 7 years old or something. And we are mostly dealing with data on how people move in cities and countries. Aggregated counts of people moving from one place to another. And our customers are mostly mobility services and transportation authorities, transport operators, who are interested in understanding the demand for the mobility services and how they can expand their services, or how they can change the city infrastructure so that it meets the needs better. And yes, so our data source is coming from the telecom companies. We are partnering with them. They give us access to data on the movement of the individual subscribers. We aggregate this data. We are not interested in the individuals in our final product. We have some probabilistic modeling. So this is the input for our probabilistic modeling algorithms. And the outcome is aggregated counts of people, how many people were at different places at different times. This is one kind of data we are calculating. And another, there is some lag, it doesn't want to change the slide. No, it's okay. So, sorry. Yes, what I want to say is privacy is very important. Privacy is very important. Therefore, we go some extra mile to make sure that in our final product it's not possible to identify the individuals. But also the data we get from telcos is anonymous. Anonymous, we don't know which individuals were producing this data. But that's not enough, because if you have locations from an individual, multiple locations, you can often re-identify them. But the data we get is also imprecise, because we only know, it's not GPS data, it's we only know the cell towers which the people are connecting. So there is a certain pretty large imprecision in this data, depending on the density of the cell towers. The data is also sparse. We're not getting regular events, but they come at some random moments in time. And data is also noisy. We are not always sure, 100% sure that the person is connected to a particular cell tower. There's a ping pong effect. Even if you are remaining stationary, but an area is covered by multiple cell towers, you get connected to one on the other. So this all makes it more difficult to re-identify the individuals. But we also make an extra effort to make it even more difficult. In our final product, we add probabilistic noise, because our modeling is probabilistic. And we do, obviously, aggregation. So we show counts for more than one person. And we do k-anonymity filtering. That means that if we have a count below a certain number, k, we just remove it from the final outcome, so that it's more difficult to re-identify the individuals. So, and it's not our goal to track individuals at all. We are focusing on aggregated numbers. And another kind of data we can produce based on this input is OD data, origin destination data. Is basically how many people move from one place to another at what time. And this is really helping our customers to understand the demand, travel demand. And OD data can be represented as a simple table with 3 columns: origin, destination, and the number of people moving. And one of the most common representations of this kind of data is a flow map, where we show on a map with arrows how many people move between pairs of locations, and the thickness of each arrow shows the number of people, is representing the number of people. And this is how one of our products looks like. It's an analyst dashboard which allows our users to answer particular questions related to this data. And for example, what are the top destinations for trips originating in specific locations? How many people travel between pair of locations at a specific moment in time? What are peak times for travel between a specific pair of locations? And what's the top mode of transport they use? And here I have a short video. So here we have an attribute, which is hour of day, and we can filter the data by this attribute, by another attribute, day, weekday, or weekend. We can also filter by the mode of transport, or by the distance traveled. And this is more or less interactive exploration of this data. We can select a certain location and look only at flows from this location, and look at how the attributes are distributed for the flows for the selected location. Yes, and as you can notice here, we have quite a few trips. This is 1 billion trips. And so the data we are working with is quite big. And therefore, in order to make this tool interactive enough, responsive, we need to make sure that the queries we are making to the data are fast enough, and that's a challenge. And I will be speaking today about how we are addressing it. So the data I showed you now was not just simple origin destination data, but it had attributes like time of day, mode of transport. And to represent it, we can use just extend this table, add new columns for each of the attributes. But this, this actually increases the size of the dataset a lot, because for each pair of locations, we need to repeat, multiply the number of rows we include in the tables for every combination of the attributes. So here is an example dataset with just 100 locations. We have 5 attributes with not that many different possible values. But can you guess how many rows does this table have? Just any guess.
We have to guess because many people know the answer.
Just a rough estimate.
Well, it doesn't have every row, right?
Right, yeah, but anyways.
Is that a spoiler?
All right, a million.
A million. Close. 1 billion. But yeah, it's like really a relatively small, not that many possibilities, but quite a large table. It's because like for every location we have like pairs of origin destination, right? So it's 100 by 100. Of course, we, as Lucia mentioned, not every pair is there, but still. Then for every attribute, there are all of the possibilities. And when you multiply this, you actually get something like 4 billion. And because not every pair, origin destination pair, is in there, because we are doing filtering, we do this K anonymity filtering. We remove rows with low counts, but still it's quite a big table. And the types of queries we are interested in are mostly these two. Like we need to draw this map. And for it, we need to aggregate the data by origin grouping by origin and destination, right? So for each pair of origin and destination, we just sum up all the flows with a certain filter condition, right? Depending on what we chose in the filter pane. And another query is the attribute breakdown. Just we are grouping by a particular attribute. Like for instance, here by hour, and we see the distribution by our own mode of transport. So, as you saw, the tables with the data we are working with are quite big. How can we ensure that the queries are performing well? That means, like, in order to support interactive exploration, it shouldn't be longer than a few seconds, right? If it's longer, then it's not good. Actually, we use Spark for the data processing, and that's good for processing huge amounts of data, but it's not fast enough for interactive exploration. Our first iteration of the dashboard used Postgres. It works fine, but it doesn't scale. So at a certain point, our data sets grew larger and larger, and we couldn't serve them anymore with the dashboard. So we looked for a different solution. We evaluated looked at a few databases, and we chose this one, ClickHouse, which is a Columnar database, which is specifically designed for real-time analytics. It's supporting SQL queries, which is nice, and it's specifically made to be able to aggregate data quickly, which is basically what we are doing in our queries. It's scalable. It means that it can run on not just one machine, but many nodes. If you need better performance, you add more nodes to your cluster, and it performs better because it splits the work between the nodes. And it's free and open source. There are other databases we looked at. One is BigQuery, built by Google. This is similar. It's also Columnar, scalable, but it has some advantages and disadvantages. The advantage is that it's fully managed. You don't need to care about data distribution, the setup of the system. You just upload your data to Google Cloud, and that's it. But here, BigQuery can be quite expensive because you pay by query, by the amount of data processed. And it doesn't have indices. That means that pretty much every query is a full scan. And so, yeah, our data sets are big and are growing constantly. So we estimated quite high costs. Also, at the point when we evaluated it, we were working with some non-anonymized data which we weren't able to upload to Google Cloud, so it wasn't a viable solution for us. There are also others. Druid, MapD is interesting because it's doing all the calculations on the GPUs, and it's super fast. It's faster than many competitors. But if you have a cluster, like the clusters with GPU are quite expensive, and also in order for it to perform well, you need to mostly fit your data on the GPU, on the GPUs in memory. So it's also kind of a limitation. So we went with ClickHouse, and we are quite happy with it so far. Yeah, so one difference between Columnar and row-oriented, traditional row-oriented database is that the data is physically stored on the disk, column by column, and not row by row. That's like in Postgres, for instance. And so, you know, if you are reading some parts of your table, right, in a row-oriented database, you need to read from the disk physically the whole blocks with all of the columns. Even if in your query you only are querying for a few columns. And it's actually our case. We have quite many columns, many attributes, but in most queries we only are looking for 2, 3, or 1 column actually. So it makes a huge difference. And in a columnar database, you just need to read the columns which are in the query. So you are, since the disk 6 the most expensive parts of the query, right? The reason from disk, that can make a huge difference. Yes, and as I mentioned, we have only a few columns in our queries. So our setup system architecture is more or less like this. We have a cluster with multiple ClickHouse nodes. We have some load balancer. We have a backend part of our application, which forms the queries and sends them to the database. And we have the front end, which runs in the browser and talks to the backend. We are using Kubernetes on Google Cloud, and that makes it quite difficult to define what kind of machines we will have in the cluster. So we have a declarative way of specifying what machines we need, what kind of nodes, how they talk to each other. We can easily replicate, like we have a development cluster and a production cluster, and they basically share mostly the same configuration. Yes, so and we don't have at the moment a lot of nodes, and they are quite slow. The low performance nodes, so that we can easily scale vertically if we needed to improve the query performance at some point. We could easily scale them vertically. Scaling horizontally is a bit more difficult because we need to, if we add new machines, ClickHouse won't handle the sharding automatically, right? We would need to re-ingest the data. That's one of the downsides, but maybe they will develop a solution in the future so that it happens automatically. But it's also possible. It just takes a bit more effort. Yeah, so we are storing our data in ClickHouse in one huge denormalized table. That's what ClickHouse is optimized for, doing aggregation, fast aggregation on huge denormalized tables. And here are some examples. So here's a data set which is not super big. We have 17 million rows. I run a ClickHouse on one node on my machine. And this query, which is similar to the queries we are using in our dashboard, took 1/10 of a second, but only 17 million rows. With Postgres, it would be much longer. So here another example, which I run in Google Cloud on 4 nodes, relatively small nodes. The data set has 1.4 billion rows, and it took 4.5 seconds to respond to this query. Processing 1.4 billion rows, which is quite okay. But this query is a little bit more complicated, but yeah, it still took a few seconds, 7 seconds, for 1.4 billion rows on just 4 nodes cluster. Yes, there is this blog post by Mark Letinczyk, who he actually evaluated quite a number of databases with the 1 billion taxi rides dataset, which was open sourced by New York Transportation Agency some years ago. And one of the databases he tested was ClickHouse, and the results were quite impressive from his tests. He wrote, "This is the first time a free CPU-based database has managed to outperform a GPU-based database in my benchmarks. It's a shame this software isn't more widely popular, as it makes excellent use of commodities hardware. Fingers crossed, this blog post goes some way to encourage those in the data community to give ClickHouse a try." So ClickHouse is not very well known, but it's actually quite a good choice in many cases. Yes, in our tool we also have a nice feature, which is adaptive clustering. So when because we have quite a lot of locations, right? If we show all of the flows all of the time between those locations, it's quite a busy view, which is not easy to interpret. That's why we do we cluster locations which are close together into clusters, And then when you zoom in and out, the cluster level adapts accordingly, right? And we actually, yeah. So there are two steps of clustering. One is done once for the locations of a data set. We cluster the locations by their distance to each other. And we calculate the center of masses weighted by the total number of flows. And then we have a cluster hierarchy, and when we store it in the database. And then, like once when we need to show it in the dashboard, we need to aggregate flows based on those clusters, right? So we just some counts belonging to the same clusters together, so that we have flows between the clusters. So we have some locations. We group them together by distance, right? Then we form center of masses, cluster centroid, and then we aggregate the flows between those, right? And then we have the clustered and aggregated flows. And we are actually doing it now in database queries, in ClickHouse queries, but it's not the most, the best way probably, but that's what we're doing at the moment. So ClickHouse has a lot of custom functions which are like can help a lot doing some non-obvious work, and one of them is this transform function. And what it is doing is that you provided two lists of values, right? And it just like for every value from the first list, it will transform it like the given value from the data table. It will transform it to the corresponding value in the second list, corresponding by the index in the list. So here we have the IDs of the locations, right? And here we have for every ID of a location, we have the corresponding ID of the cluster, right? So by providing these two lists, we can just map every ID in the original table to its cluster and aggregate the data by the clusters, right? So that's what we need to calculate those aggregated flows. The downside, it works fine. The downside is that those lists can get very long, especially if we are looking at larger areas with many locations in them. And then the queries are super long. They don't fit into the, like they're cut by in the logs or whatever. You can't easily read them. And it can also have some performance implication, providing sending these long IDs, long list of IDs. So one idea we had to improve this, which we haven't yet implemented, but it could be a possibility. So we have this cluster tree, right? Many zoom levels, and on every zoom level we have like locations grouping grouped into clusters of locations, and then clusters grouped into even larger clusters, and so on. So this is this tree, right? And we could just build a kind of trie, this data structure, where on every level we just assign some letters or numbers, digits, whatever, to every to every node on this level, right? And then we can construct a string identifying each leaf in this tree. So for every location we have this code, right, by which it can be identified in the tree. And then we could store those codes in the table, in the data table in ClickHouse. And when we need to aggregate the data, cluster the data on a certain level, we just use the prefix, like on the cluster level 3, we take the first 3 letters, right, and group by that. And then we just calculate the clusters, the aggregated counts by clusters. The downside of this would be that we are not flexible anymore in how we cluster, because now we can have multiple trees, cluster trees, right? And if we bake it into the data with the counts, we don't have this flexibility anymore. Another thing we are looking into is, which we haven't yet implemented, is to support map tiling. like in the current approach, there is a limit on how much data and how big the area we can look at. Right? And we actually have data for the whole country, but we cannot load it all in one dashboard because there are just too many flows. And what we do now is that we just have regions, multiple regions, many regions of different places in the US, and we only show one region at once, right? But it would be cool if we could just load the dashboard with the whole country and then zoom in into parts and only see data for the parts we are zooming into. And for that, we would need to support tiling, map tiling. Do you guys know what map tiling is? Like how Google Maps works? We have a grid, hierarchical actually grid of squares into which the whole world is split, right? And you have your viewport, and when you open Google Maps or whatever, Sleepy Map, Web Map, you use it only loads data for the tiles. Tile is like one square for the tiles which intersect with the viewport, right? And on the zoom on the corresponding zoom level, if you zoom in, you will be loading smaller tiles, data for smaller tiles, which is more precise, right? More fine-grained, showing more individual items, but only covering this like the part which intersects with your viewport. This way, you don't have to load the whole world into your browser, right? Which wouldn't be possible. Like OpenStreetMap is how big? 50 gigabyte, right? For the whole world. And we don't ask users to load the whole world into the browser, but they can zoom in into regions which they're interested in, or zoom out and look at the whole world on a very low grain level, coarse grain. So we could actually do the same thing with the arrows, right? We could just only load into the browser and query it from the database the arrows which either start or end in the particular tiles which we are looking at, which our viewport intersects with. And when we zoom out, we could also employ clustering to get high-level data, not very precise, but aggregated on a high level. So the combination of map tiling and clustering would work. And geohashing, do you guys know what geohashing is? Some? I'll try to explain. So geohashing is actually a way to encode geographic coordinates. Like there are two coordinates, right? Latitude and longitude. You can produce a geohash is a code which actually encodes it in one string, right? And the nice property of this code is also that the more precision you need, you just make it longer, right? You add more letters to it, and then it will be more precise. And and the hierarchy, there's a hierarchy, right? If you cut some letters, you will get the larger square, which contains all the locations which have longer codes, but with this prefix, right? So there is it's a nested system, so that if you, like for any given needed precision you want to get, you can have just a code, right, which will give you a square. Basically, it's a way to encode those squares in the same system, right? We could look at it on this. So every square would have a code, and like this square has a code ABC, for instance, right? Then this square would have the code AB, and every square which starts with AB would be inside of this square with the code AB, right? And so it's actually similar to this approach I explained here, but for clustering we wouldn't use the squares, because the cluster tree is different. It's not based on squares. It's based on how close locations are to each other. Right? That's a bit different. But the idea would be very similar. We could store 2 additional columns here for the geohash of the origin and destination, right? And then if we want to load data for a specific square on a specific zoom level, we just need to look for the prefix, check the prefix of the geohashes, and we can just substring take the first 5 letters of the code, right? And then we can group by that, and then we get aggregated counts for the data in this square. Or we can filter by the square. Yes. Yeah, there is another post from Carto. It's the company which they develop an analytics tool, geographic data, for geographic data. And they also played with ClickHouse, and they played with quad key, which is very similar to geohashing, in order to be able to filter data in ClickHouse, which doesn't have much of geographic functions support, but you can, using quad key, you can filter data by bounding box, for instance, efficiently. And they showed an example. They just store the quad key instead of storing latitude and longitude for every data entry. Then you can filter by some kind of range, right? If you are looking for a bounding box, and that's quite efficient. Yeah, as I mentioned, ClickHouse doesn't have much support for geographic functions, but there are a few. For instance, it actually supports geohashing. You can convert between latitude and longitude to geohash and back. Yes. Yeah, they're also working on an interesting indexing approach, Z-curve. This is a PR from ClickHouse source code, GitHub repository. And they are working on this Z-curve index, which allows basically to index multiple columns into one index, right? So Z-curve is a way to enumerate, like if you have 2 variables, 2 dimensions, right? For instance, latitude and longitude. You can enumerate them into one dimension. It's also similar to geohashing. But the point is that if you add such an index for latitude and longitude, then the data will be organized in a way so that it will be more performant to query for a bounding box, for instance. But it's not yet implemented. So, but if it was implemented, then we wouldn't even need to add the two additional columns for the geohashes of the locations. So, yes, so we actually open sourced a demo app which uses our presentation of the OD data and ClickHouse as a backend, just to demonstrate the approach. It's somewhat similar to our actual dashboard, but it's very limited in functionality, but it demonstrates the basic approach. So you can find it on GitHub. Yeah, it looks very similar to what I showed you before in our actual dashboard. You can look at the map, zoom in and zoom out. There is clustering support. Then you can pick attributes and filter by them. And every view actually sends a separate query. Like this view sends a separate ClickHouse query. This view sends a separate ClickHouse query, and the map, of course. And there is a short description about how this can be set up on DigitalOcean. So you can buy the cheapest, pay for the cheapest droplet on DigitalOcean. It's a cloud provider. Install ClickHouse there, and then run the application there. Ingest the data. This is New York bicycle sharing data, which is publicly available. So if you are interested in the approach, you can play with it. that's pretty much it. There's also a blog post which we recently published about the same stuff I talked today on Medium, so you can look at that. And yes, that's it. If you have questions, I'm happy to answer.